Okay, today I'm going to talk to you about magnetic bumps in porphyry copper mineral systems and how they can help with exploration. I'll use data over the Pebble porphyry copper gold moly deposit in southwest Alaska as an example. Here's a map of northwestern North America showing Canada onto the east and the U.S. state of Alaska to the west. Pebble is about 320 kilometers southwest of Anchorage. My goal for this presentation is to get you to think in new ways about bumps observed in aeromagnetic data when exploring for porphyry copper systems. I'm going to do this first by giving you some background information, then we'll look at the geologic setting and the aeromagnetic bumps near Pebble. Next we'll step out and compare the Pebble district with the Pike Creek area using lower resolution aeromagnetic data, and then we'll look at other intrusion-related resources within the region, and then finally we'll figure out what this means for exploration. So aeromagnetic data are commonly available at little or no cost from government surveys. These data may be provided as compilations or as individual surveys, with both having advantages and disadvantages. The compilations are usually GIS ready and so can be easily integrated with other exploration data. However, significant processing occurs when compiling these data sets, which may result in loss of geologic information. Individual surveys, on the other hand, tend to provide higher resolution data and may contain more geologic information. However, their aerial extents may be limited. Utilizing both allows us to observe bumps at multiple scales. Here's an overview of the Pebble deposit looking to the northwest. The deposit is around 4 kilometers wide and outcrops in the west, but is covered by glacial deposits and younger volcanic rocks to the east. The discovery outcrop is only about 100 meters long, and so the porphyry copper system has a limited surface expression. In 2007, the USGS began a collaborative effort with the Pebble Limited Partnership, trying to develop ways to detect mineralization undercover as part of the Concealed Deposits project. And this talk presents some of those results. And so I'd like to say thank you to the Pebble Limited Partnership for the support. These photos illustrate some of the challenges with exploration in southwest Alaska. For one, there's plenty of cover material to look through, including younger rocks, vegetation, and quaternary deposits. And then the outcrops can be very limited, which makes traditional geologic mapping difficult. The area is also very remote, so gaining access is expensive as helicopters are the main mode of transportation. Conceptual models of porphyry copper deposits and convergent margins are a good starting point for understanding mineral systems. Here are two recent ones from the economic geology literature. The top diagram shows an intraoceanic arc that developed on ocean crust. Between the craton margin and the island arc is a back arc basin in which extension may lead to the formation of linear ridges. In this setting, the porphyry copper epithermal systems form in the intraoceanic arc, and the Alaska-type Ultramafic-mafic complexes form towards the base of the arc. Volcanic-hosted massive sulfide deposits may form along the extensional ridges in the back arc, and this sort of setting is pretty straightforward. The bottom diagram shows a more complex situation when terranes accrete to the craton margin. In this setting, many different granitoids and related mineral deposits may form as the margin evolves. The oldest deposits may be those associated with the construction of the intraoceanic arc. If the island arc accretes and the subduction continues, then a continental arc and associated porphyry epithermal systems may form. As the lithosphere and asthenosphere evolve and the continental crust thickens, melts may be generated that lead to intrusion-related gold and granitoid tin tungsten deposits in the back arc and craton margin. All of these stages would compose the mineral system, in my perspective. And it is this more complex system that we see in Alaska. The porphyry epithermal environment is a relatively small expression of a much larger system. The porphyry copper deposits are associated with magnetite series granitoids. Such rocks have significant amount of magnetite as an accessory mineral. If the granitoids are placed in the country rock with little or no magnetite, then these igneous rocks may produce bumps in our magnetic data. Okay, so now let's talk about the geologic setting of the Pebble deposit and relate high-resolution aeromagnetic data to the rocks mapped in the Pebble district. Here's a lithotectonic terrain map of southern Alaska. Anchorage is over here. The Pebble deposit is down here to the southwest. Southern Alaska is composed of several island arc complexes that run across like this. These had amalgamated by Middle Jurassic and accreted to the continental margin by Middle Cretaceous. Landward of the island arcs is a series of foreland basins shown in red. These basins host the Middle Cretaceous porphyry deposits, including Pebble down here. We'll focus mostly in this area. So let's see, here's a map of the Pebble district, a geologic map of the Pebble district. The Pebble resource is outlined over here. Some geographic features include the Kaskanak Mountain to the west and then Koktuli Mountain over here in the east. Walking through the geology, the oldest rocks include sedimentary rocks, basalts, and related gabbroic intrusions that outcrop along the edges of Kaskanak Mountain. Around 96 million years ago, diorite and granodiorite sills were in place and cut by younger alkalic intrusions. These intrusions include a biotite peroxenite unit that is not well studied but has mineralogy suggestive of an Alaska-type Ultramafic-mafic complex that we'll talk more about later. Around 90 million years ago, granodiorite intrusions formed the batholith that underlies Kaskanak Mountain. And then also at 90 are granodiorite stocks related to Pebble and the other mineralization centers that include skarn and porphyry copper throughout, mostly surrounding Kaskanak Mountain there. And then from 90 to 65 million years ago, mafic to felsic volcanic and sedimentary rocks were deposited off to the east. And then around 65 million years ago, monzonite intrusions came up through the area. And then at 46 million years ago, felsic intrusions and volcanics and associated low sulfidation epithermal systems formed over on Koktuli Mountain. And then recent times, glacial material covered much of the area. So it's a very long-lived magmatic center in the Pebble district there. So let's look at the reduced to polar magnetic anomaly map shown here. The flight lines were flown northwest and spaced 200 meters apart with a nominal terrain clearance of 60 meters. Also shown is the line work from the geologic map. Pebble resources again is over here, Kaskanak Mountain here, and then Koktuli over here. The aeromagnetic data appear to differentiate some of the igneous rocks in the district. The older basalts and associated gabbroic intrusions show up as magnetic highs in the south and north ends of the district. And then the alkalic intrusion and the biotite peroxenite units show up as major magnetic highs right there in the center. And then the granodiorite batholith appears as a moderate long wavelength high, although the anomaly is not closed off to the west. And then younger basalts show up as moderate short wavelength anomalies. And let's see, the younger monzonite intrusions and related volcanics to the east show up as magnetic lows. So the RTP map does not clearly image the hydrothermal systems. However, they do highlight some of the plutonic rocks that formed as part of the porphyry copper system, in particular the granodiorite batholith off to that underlies Kaskanak Mountain. So the plutonic rocks are well imaged in the Pebble district. Let's step out and compare nearby plutonic rocks using lower resolution data that we have that cover the entire region. So why compare these two areas? Both areas have outcrops that have been recently mapped. Both areas have modern age dates that indicate the younger Pike Creek rocks to the west are similar in age to nearby intrusion-related gold systems. Magnetic susceptibility measurements are available for both areas, and then we also have continuous aeromagnetic data that covers both areas. Let's look at the map geology in the region. The Pebble deposit is outlined over here, Cascanac Mountain over here, Cockatooly Mountain there, and then Groundhog Mountain up here. Then the Pike Creek area is about 50 kilometers west of the Pebble district. Stepping through the geology, the oldest rocks are sedimentary, basalt, and related gabbroic intrusions, as well as volcanoclastic rocks. Then we had Middle Cretaceous plutonic rocks of intermediate to ultramafic compositions that occur in and around Cascanac Mountain. These are the ones that are related to the Porphyry copper systems. And then Late Cretaceous felsic to intermediate plutonic rocks occur in the Pike Creek area to the west, as well as on Cockatooly Mountain. There's no known mineralization in the Pike Creek area. We also have tertiary felsic to mafic volcanic rocks that occur throughout, and then a significant amount of glacial deposits blanketing much of the geology in the area. So here's a look at the aeromagnetic data that were collected along flight line space 1.6 kilometers at a nominal height of 300 meters. The data were merged from 5 surveys to form a continuous data set over the region. The reduced pole transformation shows that the magnetic highs are predominantly within the Pebble district. The magnetic highs over the outcropping granodiorite on Cascanac Mountain is now fully imaged. We've closed off the anomaly over here. Additional similar amplitude magnetic anomalies occur to the north underneath Groundhog Mountain. The Pike Creek area over here, although similar rock compositions but of differing age, show up as dominantly magnetic lows. So these data show that similar composition rocks, such as granite and granodiorite, that formed during 2 different time periods within our mineral system, exhibit contrasting magnetic signatures. Magnetic susceptibility measurements show that although these similar rock compositions occur in both areas, the older rocks in the Pebble district have relatively higher susceptibility values than their younger counterparts in the Pike Creek area. If we were to plot them back to the USGS classification scheme where these rock names originate, we'll see no correlation between the rock type and magnetic susceptibility values, which really makes sense because the classification scheme does not take into account magnetite content. What this does is illustrates the importance of utilizing magnetic susceptibility measurements when interpreting the aeromagnetic data. So here's a look at the distribution of magnetic susceptibility measurements, which shows correlation between the magnetic anomalies and the magnetic susceptibility values from the plutonic rocks that formed during the 2 time periods. If we were to take a look at the upward continue data here, the upward continuation transform calculates the magnetic field at an elevation higher than that at which it was originally measured. In this case, it was 300 meters. So what effect this has is it attenuates the near surface anomalies and accentuates the anomalies from deeper magnetic sources. And you can see that these data are mostly imaging rocks in the Pebble district over here. The anomaly is centered over the granodiorite batholith that underlies Cascanac Mountain. If we were to take a look at the total horizontal gradient of this upward continue data, that's what we're looking at here. The high gradient maps relatively deep magnetic contact that runs along here. This deep magnetic contact encompasses the Middle Cretaceous hydrothermal systems down here, including the Pebble deposit, and extends continuously well north of Groundhog Mountain. This deep magnetic contact may be the footprint of our porphyry copper system down here. We could do some 3D inverse modeling to help us understand the magnetic sources that are generating this footprint. This slide shows 3-plan view depth slices through the preferred inversion results. The white line The white lines indicate a isosurface chosen to represent the contact between the granodiorite and the non-magnetic sedimentary host rocks that we found around Cascanac Mountain. At 1,000 meters depth, several near-surface magnetic features are imaged that include the granodiorite on Cascanac Mountain, and then rocks that may underlie the mapped basalt beneath Groundhog Mountain. And then the isosurface parallels the outcropping patterns, which gives us a little bit of validity to our inversion results. At 5,000 meters depth, many of the shallow magnetic features have converged into three main magnetic sources. And then at 9,000 meters depth, the magnetic areas have all converged into one body that is mostly within the footprint of our porphyry copper systems. That was imaged within the upward continue data. It's unlikely we'll ever know what lies at these depths, but the math and the physics at least indicate highly magnetic material underlies our known porphyry copper systems. So now that we have a better understanding of the magnetic bumps in the Pebble district, let's step out and use these same data to look for other parts of the mineral system. Here's a simplified geology map across the convergent margin. The Alaska Aleutian Range is over here to the east, and present-day volcanic activity occurs at Iliamna and Augustine volcanoes. And we just looked in detail at the Pebble Pike Creek area right here. Stepping through the geology from older to younger, we have Jurassic and older mafic, ultramafic volcanics and intrusions within and to the west of the Alaska Aleutian Range. And then the Jurassic intraoceanic arc rocks include intermediate to ultramafic plutons that are overlaid by volcanic rocks in the Alaska Aleutian Range to the east. And then we have Middle Cretaceous to Late Cretaceous sedimentary rocks that occur to the west, shown in green. And then Middle Cretaceous intermediate to ultramafic plutons intrude the sedimentary rocks. And then Late Cretaceous to Paleocene volcano-plutonic rocks intrude and overlie the sedimentary rocks further to the west. And we also have Tertiary felsic to mafic volcanic rocks that are widespread west of the Alaska Aleutian Range, shown in tan there. And of course, we've got Quaternary deposits covering much of the area. The structural trend is generally northeast and includes the poorly understood Mulchetna Fault up here and then the Lake Clark Fault down here. These structures trend parallel to the suturing of our intraoceanic arc over here. Also plotted are some of the better understood mineral deposits in the region. The older prospects include the porphyry, copper, and Alaska type complexes and volcanic hosted massive sulfides over here associated with the Jurassic Island Arc Complex. Then we have Middle Cretaceous prospects that include Pebble down here and the Nikola porphyry copper system up here. And then we also have Alaska type complexes near Pebble and then over here at Kamek to the west. The younger prospects include reduced intrusion-related gold systems up here at Shotgun, and then granitoid tin tungsten prospects over here at Sleetat. So taking a look at the reduced dipole aeromagnetic data over the broader region, we can see a complex pattern of magnetic highs over here associated with the intraoceanic arc rocks in the Alaska Aleutian Range. A broad, moderate amplitude magnetic high with dimples of magnetic lows occurs over the more landward rocks northwest of the Mulchetna Fault. These may reflect the craton margin. Between, we can see several clusters of magnetic anomaly highs that run northeast along the Lake Clark Fault, which include the anomalies we found in the Pebble district. What is apparent is that the igneous rocks associated with the Pebble deposit have very different magnetic signatures than the Alaska type ultramafic complexes over here at Kamek. as well as the younger intrusive rocks at Shotgun and then the Pike Creek area that we looked at earlier. The Shotgun area shows a central low with an annular high that has been attributed to pyrrhotite and hornfels rock. And then the Sleets Hat granitoid tin tungsten prospects are associated with linear magnetic highs and lows that occur along trend of the Mulchatna Fault here. The upward continue data shows highs over the interoceanic arc rocks in the east and more isolated highs trending northeast along the Lake Clark Fault. Plotting our radiometric age days for plutonic rocks shows that the magnetic highs along the Lake Clark Fault have associated Middle Cretaceous igneous rocks shown in red as red squares. In general, the radiometric age days for the younger plutons shown as green squares plot on magnetic lows. If we plot the total horizontal gradient that represented the footprint of the porphyry copper systems in the Pebble district, we can see that these deep contacts occur throughout the region in both linear and circular geometries. And then think about our porphyry copper deposits forming in a linear origin parallel belt. We can interpret this linear trend of footprints as being our footpath for the porphyry copper systems. However, we also have Middle Cretaceous rocks associated with these anomalies that are off trend of the inferred magmatic arc, so we need to figure out what these might represent. The Alaska Resource Database file indicates the presence of Alaska-type Ultramafic-mafic complexes along the Alaska Aleutian Range and then over here at Chemic. These resources form in belts along the island arc complexes. They potentially host several commodities. The plutonic rocks are highly magnetic, and the rocks have small areal extents of only a few kilometers. Fortunately, we've got some drill hole in Chemic, which tells us these intrusions are zoned from outer peroxenite units to inner gabbros, all of which have high magnetite contents of 10 to 20%, 9%, and 3%. In addition, we know that these resources are relatively shallow. So these shallow magnetite-rich rocks should produce a characteristic short wavelength, high amplitude magnetic anomaly. Near Chemic, over here, these characteristic anomalies are easily recognized in both the gridded and profile data sets. In the profile, in the Pebble district, the elevated magnetic background makes them less obvious in the gridded data. However, we do see them quite well in the profile form. So what we can do is use the original flight line profile data from the individual surveys to map these characteristic anomalies. Here are the results with black triangles indicating characteristic anomalies. The top row up here shows the more isolated anomalies that were in the western part of the study area that were off trend of our magmatic arc, while the bottom row shows anomalies within the porphyry copper footprints mapped along the magmatic arc. What we see is nearly all flight lines map the characteristic anomalies over the more isolated anomalies up in through here. Let's see. And then only a few anomalies are mapped within our porphyry copper footprints down here. There isn't anything known about those over here near Auden, but in the Pebble district, the mapped anomalies occur over the biotite peroxenite unit and the Scarn prospects to the south, and some unknown things up here at Groundhog Mountain. What's really important here is that not all anomalies within these porphyry copper footprints are mapped. This indicates that there is a fundamental difference between the magnetic sources beneath the porphyry copper footprints and then these Alaska-type Ultramafic-mafic complexes that were both well imaged in the upward continued data. So lineaments. Lineaments can help us understand the magnetic structure of an area. These lineaments may not be evident in the RTP data. We chose the tilt derivative to highlight magnetic lineaments. We can see the texture changes proximal to the Mulchatna Fault over here. and down towards the granitoid tin tungsten prospects over here at Sleetek. The continental rocks are off to the northwest, and then the oceanic rocks to the southeast. And then, let's see, plotting the mapped ocean floor rock shows that they follow a long trend of several of the lineaments. The Tilica-Kilia complex over here in the east has been interpreted to have formed in a supersubduction zone setting associated with the onset of the Jurassic Island Arc complex. These rocks host at least 3 reported potential VMS occurrences. And then additional lineaments may be favorable for VMS systems off to the west, or alternatively, they could simply be telling us the extent of the back arc in our mineral system. We also see a lot of circular features within the continental margin rocks to the northwest. The Hornfels rings around the intrusion-related gold prospects as Shotgun is highlighted nicely, and then additional circular anomalies may reflect granitoids and other intrusion-related gold systems in the continental rocks off to the northwest there. So let's pull this all together and see what it means for exploration. The aeromagnetic data provide a continuous set of observations across a large swath of land over the convergent margin. Magnetic susceptibility measurements helped us understand the granitoid rocks and the bumps that they produce. Placing these bumps within our conceptual models indicates where we are in the mineral system down here. And what this should do is lead to a better informed exploration program. When we go out there to get our boots on the ground, we might have a better idea of what we're looking for. Let's take a look at the bumps across the mineral system through the evolved convergent margin. The geology map on the bottom here shows the Jurassic Island Arc rocks in purple. The subduction trench was off to the east over here. And so a back arc likely existed to the west. The Middle Cretaceous plutonic rocks are shown in red with an inferred back arc off to the west. These rocks formed after the accretion of the island arc and so may represent a continental arc. Late Cretaceous plutonic rocks shown in pink are mostly west of these Middle Cretaceous. Let's see, mostly west of the Middle Cretaceous rocks and extend into our continental margin. So thinking about the magnetic data, the reduced to pole data show a complex pattern over the intraoceanic arc and continental arc up here. Within this complex pattern are characteristic short wavelength, high amplitude anomalies that might indicate magnetite-rich Alaska-type Ultramafic-mafic complexes. And then the late Cretaceous rocks to the west have little magnetic expression. If we were to upward continue the data, we highlight the intraoceanic and continental arc rocks off in the east. And then taking the total horizontal gradient helps define the footprints for our porphyry copper systems. And then the tilt derivative shows another complex pattern. We've got high frequency anomalies off to the east over the magmatic arc in the back arc setting. And low frequency anomalies are more common over the craton margin over here. The tilt derivative highlights the Hornfels rocks around the Shotgun deposit very well, and may be providing a footprint for intrusion-related gold systems within our continental margin. Proximal to the change from high to low frequency anomalies are our granitoid tin tungsten prospects at Sleetek, and we need to remember that these form near where the back arc and the craton margin meet. So returning to our lithotectonic terrain map of southern Alaska, we have these island arc complexes that accreted to the continental margin on the landward side of these foreland basins shown in red. These host the Middle Cretaceous porphyry systems. And We use high-resolution data to show that the granitoids related to the Pebble deposit produce significant bumps. Linking these observations with the lower resolution data identifies several footprints for porphyry copper systems over here all the way up to Nikola. And then we can do the same filtering using a broad-scale aeromagnetic compilation to show that, that a 700-kilometer-long footpath for our potential porphyry copper systems exists up over here. So we just saw that porphyry copper mineral system can produce many different magnetic bumps. The distribution of these bumps helps us understand where we are in the system, which ultimately leads to better informed mineral exploration programs. What we found is no single filtering or modeling approach solves all problems, but collectively a more complete picture of the mineral system is obtained. Footprints and footpaths of our porphyry copper systems can be imaged at broad scales. The aeromagnetic data help differentiate granitoids with differing mineral deposit styles across our evolved continental margin. The modeling suggests that lots of magnetic material beneath the porphyry copper systems exists. And then we also saw that the Alaska-type complexes produce characteristic anomalies that are easily mapped using flight line data. Perhaps these are good targets to put us in the right ballpark. And then the lineaments observed may reflect extension in the back arc and the potential for VMS deposits. And that's about all I had to say.
Thanks, Eric. We got a time for a question or two. I can relay them. Dave?
How much uplift and erosion has there been in the Pebble deposit? So what level are we looking at in the original porphyry copper system?
Dave Clark is asking how much uplift is in the original Pebble deposit.
Well, there is no high-level epithermal systems, and so those have all been eroded away. There is, I can't tell you a precise number, but I would say that at least the high sulfidation epithermal systems that we typically think are above the porphyry copper system have been eroded away.
So a minimum.
What's the alteration that's exposed at the surface?
Oh, I guess, yeah, by proxy, what's the alteration you've got at the surface as a proxy for depth? Dave's asking.
Let's see, at the surface there are QSP alterations surrounding the deposit. You even have some shallow level K-spar magnetite alteration, which also occurs much deeper off to the east at 1,000 to 1,500 meters depth.
Okay. Yeah.
But there is some propylitic alteration that occurs within a graben system on the eastern side of the deposit. But it's several hundred meters deep.
Okay, maybe the order of 1.5 kilometers, 2, something like that? Yeah.
I think that's reasonable, yeah.
Okay. All right, anybody else? Wrap up and we let Eric go for a scotch? All right, okay. Thanks very much, Eric. We really appreciate you coming in this way, and we'll let you get on with your evening, and we'll be signing off here, and we'll be in touch, okay? Thanks very much.
Okay, thank you.